Welcome to the digital classroom. We're doing some more interview prep. Here we are looking at LEET code question 912, sort and array. And with this type of question, or in every interview question, we always want to, first of all, clarify our inputs and our outputs with our interviewee or interviewer. And we also want to make sure we understand the question. So I would repeat the question back to them. I would ask them, I would say something like, okay, so you want me to take an input of nums and you want me to sort that in non-decreasing order. And you want it to be an in log in time with the smallest space complexity possible. And then I would verify the inputs and the outputs. So we're returning an array of integers, and we are expecting what kind of inputs. Do we have positives? Do we have negatives? Do we have duplicates? Those are the type of questions I would ask with this one. And with this one, we do. We have negative numbers, we have positive numbers, we have, going up to a size of 10 to the 4, which means this needs to be faster than n squared. And so I would then start brainstorming some of the ideas for this solving this problem. And this is a sorting problem. So there's a lot of sorting algorithms that you should know off the top of your head. And a few of them are a few of the more popular ones: insertion sort, bubble sort, selection sort. We also have merge sort, and then quick sort and bucket sort. And then I will go over some of the trade-offs with these. So a lot of these are not very efficient. So for example, bubble sort is n squared logarithm, and selection sort, insertion sort are also n squared. However, insertion sort, when the input is mostly sorted, this is actually O of n. So it's the best case scenario of O of n, but worst case, or I think it's average case of n squared. Merge sort, we got to the n log n, and as well as n log n for quick sort. And quick sort can also get up to, well, n log n, let's just say n log n for now. And bucket sort, probably one of the faster ones, depending upon the inputs. You can get a best case scenario of n and worst case scenario of n squared. So then we have to kind of discuss some of the trade-offs with the interviewer. So like, for example, the two best ones, I think, for this one would either be merge sort or quick sort. One of the problems with quick sort is faster than merge sort, even though they're both n log n. Quick sort it usually runs a little bit faster than merge sort. But the problem with quick sort is that it's not stable, which means that if we have duplicates, they won't keep the same order among the duplicates. And merge sort is stable. But since this problem is asking for the smallest space complexity, we can probably do quick sort in place. And so I'll go ahead and just go ahead and code up that one. So we're going to do quick sort in place. And to do this one, we're going to have a helper function where we're going to take, pass in the input array, and then we're going to have a start and an end index. And our base case for this is if start is greater than or equal to end, then we return. Okay, and so again, that's the base case. So this is the case where, get to our smallest input. And then our recursive case is going to be, so let me explain this one a little bit, because it also helps me to code it up when I have a small visual that I can look at it. So let's say that this is my input array, and I'm going to say 3, let's say 4, 1, and then 2, 5. Okay, and so with the input array like this, what we're basically doing with this, this is a version of Lamoto's, I don't know how to say it, partitioning. And so we're going to have a couple pointers here. We're going to start off with all of our pointers at the beginning, but we're going to have 2 pointers. It's going to be a little tricky to do 2 pointers with this example. but I'm gonna try. So we're gonna have a smaller pointer and a bigger pointer, and they're both gonna start off both pointing at the beginning. And so we're gonna have a pivot. So the way this logarithm works, we pick a pivot point, a pivot number, if you want to say, and we're gonna swap that to the beginning. So it's going to be some random index from any of these numbers. And that's the reason why they use random index, is just because it makes it a little bit faster. It doesn't, we don't have a skewed one-sided tree, which will make this n squared. And so let's just say I picked the number and I swapped it, and so our pivot number is 3. And then we're going to have our 2 pointers, like I said, a smaller point. I'm going to call 1 pointer smaller, 1 pointer bigger. And then we're going to increment the bigger pointer. Okay. And so the bigger pointer is going to increment, and our smaller pointer will stay there. And as the bigger pointer increments, is going to say, okay, is this number smaller than our pivot number, right? So the pivot number is at the beginning, remember? And so 4, it is bigger, so we don't do anything. Anything that's bigger than our pivot, we're not going to do anything. But if it's smaller than our pivot, and so it increments. And so if it's smaller than our pivot, what we're going to do is we're going to increment our smaller and then swap the bigger and the smaller. So then we're going to swap this. So it'll be 1 and 4. And so what we're doing is we're creating this partition where we have all the numbers that are smaller than our pivot number on the left side, and all the numbers that are bigger on the right side. So, so as we keep on going, so it goes, and it's like, okay, so this number is smaller than our pivot. So what we're going to do, we're going to increment our smaller and then swap bigger and smaller. Okay, so we're going to swap these two. So this will be 2, and then this will be 4, and then we're going to keep on incrementing. And so then this is bigger, so it keeps on going. And so what the end result is that you have all the smaller numbers on the left side and all the bigger numbers on the right side from the original pivot number. And then at the end, after bigger has gone off the finished the for loop, we're going to swap beginning and the end. So see. So then we're going to swap the 2 and the 3. So this would be 2, and then this will be 3. And then, so that would give us, so everything to the left of the 3 would be unsorted. Everything to the right is unsorted, but it's all bigger than, this pivot number, right? And so then it's going to repeat that. So it's going to pick another index, and it's going to do that again. And we're doing this recursively with this helper function. So then the next index, for example, would be, just this, the 2 halves, right? So then we're going to, pick we're going to, as a middle manager, we're going to give the rest of the problem to our subordinates. So we're going to say, hey, you go and take care of index 0, 1. You take care of index, will that be 3 and 4? And it's going to keep on going. All right, so that was a lot. That took too much time to explain, but it's good to help with when coding this up. So first thing we're going to need to do is to pick a random number. And so we're going to do that with Python with random, and then it's going to be between start and end. And so then, or we could call that pivot, like just to keep the naming similar to what I just said. So that'll be our pivot number. Okay. And so then we're going to swap that pivot number with the start, wherever the start is for this this portion of the array, because again, it's going to be the same array. We're doing this in place, so we're just going to keep on picking smaller portions of this array. And so in Python, we can quickly swap by doing this syntax. Okay, so we swap it. We also need to initialize our smaller pointer, which will be start. And then we do our for loop, bigger. And we're going to go from start +1, because we're not starting directly on start, but we're going to start a number it. And we have to go one more because just how Python works. So bigger in range and start to unit. And so if a of bigger, bigger is less than a of start, this is our pivot point, then we're going to, like I said, we're going to increment the smaller pointer, and then we'll swap. So swap the smaller with the bigger. And again, this is the way we just quickly swap in this syntax for swapping in Python. And if I could type correctly, smaller. Okay, and so that's going to run through all the way to the end, like we said. And then once it's finished, we will swap our start with our smaller. And then we have to call the helper function a couple more times. And so we're going to basically, so this is the recursive part. We're recursively calling the function on a smaller part of the original function, right? So we started with from start to end. So now we'll do, we have our pivot point that we picked. So it will be from, we're going to still pass on the same array that's in memory. So we're doing this in place. And then what is our pivot point? We're going to go from start to pivot -1. And then we'll do the same thing for the other half of the pivot +1. Because remember, our as the partition goes, now that's why it's called a partition, because this element is now in its final place. So we want to pass, pivot -1 and pivot +1 to the rest of our subordinates so they can do the rest of the work. And that's going to go to the end. Okay, and then we have to call the function. So this would be, we're going to call helper on nums, and it's going to go from 0 to n-1. And we just return nums because should be in place. So again, it's a good thing to go through your code and kind of run it without, because some interviews don't have a working IDE, so you can't run it. So you have to kind of just run through it. Random int, I believe that's the syntax. Yeah. Start pivot, we switch them, and then we assign the smaller as a pointer. Our bigger pointer is going through the for loop. And if the bigger is less than the start, good, we increment the smaller half, right? Just like we did in the example above, we swap them and we keep on, and then the bigger keeps on going all the way to the end. And once it gets to the end, we swap the start and the smaller. Yeah. And then we recursively call the function on a smaller portion of the same input all the way to pivot -1, pivot +1. It looks good. Let's run it. See how it goes. Looks like we got one wrong answer. 0 came in there. Duplicates. So I'm trying to find being able to find out your error is also something that takes time. I'm kind of thinking it might be related to this pivot because we assign pivot. No, it should be fine. Nums a start is greater than or equal to end. 0 nums. So it looks like the 0 got placed in the wrong place. Looks interesting. I think this is I didn't feel like this pivot was the right. I think, yeah, that works. All right, let's run it, submit it. And again, so this code is good because talking about space and time complexity, um, this is for time. This is not fast enough. Hmm, lots of duplicates, which is probably why this code, because like we said, quick sort is good for if it's not a lot of duplicates. If it's a lot of duplicates, it's going to become n squared because then the tree becomes lopsided, and so it's just this you know your the tree that you're building is one-sided, and that's the whole reason for picking the random indexes to avoid that. So yeah, this doesn't work well with quicks with you know duplicate inputs, and so this is the situation. But it works really fast. It is faster than merge sort if it's if it doesn't have if it's truly random. So I think we're gonna have to go with merge sort, and I have a separate video on that. So I think I'll just stop here and point you to that one. But because I'm not gonna code it up right now because I already coded up in another video. So that's it. This would be O of n log n, big O. Um, but in this situation where you have multiple duplicates, like I said before, that's when the time complexity increases. Also, this another good thing about this is that the space complexity is going to be O of 1 because we're doing it in place. Whereas with merge sort, we have to use recursive call stack, which would at least be O of log of n, and using the temporary array, auxiliary index temporary array in merge sort is going to be O of n. So it's a trade-off. That's how it is with coding oftentimes. I hope this helps. Wish it would have worked, but it didn't work, but that's okay. This is how it is when you do live sessions. If you're anything that you can help out with, if there's anything that can make this better, please let me know. I would definitely appreciate that. I'm learning this as well. And good luck on your interviews, and talk to you guys later. Adios, mi amigos.